In this video, we are going to look at a simple ideal transformer. It may seem like we're jumping into the middle of a lesson, which we are. However, there is only so much that you can do in this short time frame. The takeaway, however, from this video are a few fundamental facts, which are the turns ratio of a transformer and how it relates to the primary and secondary voltages, currents, and impedances. If you want more detail around these fundamental facts, you can find them explained in more detail in my courses located in my stand store, which may be found at this location: https://lowercase stan.store/uppercase G uppercase V uppercase B.
If we wind two coils on a steel core, we can cause almost all of the flux to link both coils, and we can further hypothesize the case in which 100% of the flux is linked by both coils. In this ideal case, it is called an ideal transformer. Now, let's input a sinusoidal AC voltage on the red coil on the left. This is known as the primary winding. This AC voltage will cause a small current to flow in the primary coil. The amount of current flowing is limited by the reactance of the primary coil. In an ideal transformer, this reactance is 100% inductance, so the current will lag the voltage by 90 degrees. This current is known as the magnetization current. Remember that any time a current flows, it will produce a magnetic flux proportional to it, which means it too is sinusoidal and in phase with the current. And since we are dealing with an ideal transformer, all of that flux flows in the iron and links both coils. Considering the primary coil, we will measure a voltage drop. This voltage drop we'll call V1 across its terminals, and it will be equal to the applied voltage, VAC, because it's directly connected to the applied voltage. In coil 1, the flux produced by the generator is related to the voltage V1 by Faraday's law, which involves the changing flux times the number of turns in the primary coil. In the coil 2, the secondary coil, the voltage produced by that same flux by mutual inductance is also given by Faraday's law, which involves the same changing flux but times the turns in the secondary coil. That voltage is either larger or smaller than V1 depending on N1 and N2, the turns of the primary and secondary coils, but it is in phase with the applied voltage VAC. Mathematically, we can rewrite the two Faraday law equations for both the primary and secondary coils, keeping only the associated voltages and coil turns numbers on the right-hand side of the equations. As you can see, both the right-hand sides are equal to the same changing flux, minus d phi by dt. Therefore, we can write minus d phi by dt is equal to V1 divided by N1 is equal to V2 divided by N2, which means V1 all over N1 is equal to V2 all over N2. Or rewriting it, we can see that it's V1 all over V2 is equal to N1 all over N2. These two ratios, V1 to V2 and N1 to N2, are known as the turns ratio of the transformer, and sometimes it is designated with the letter A. Now let's add some impedance to the secondary coil of the transformer. We know that the voltage drop across the impedance will be V2 and that it is in phase with the applied voltage VAC. By virtue of Ohm's law, a current will flow in Z2 whose magnitude is given by V2 all over Z2. And depending on the impedance Z2, the current will either lead or lag or be in phase with the voltage V2 and VAC. The current in Z2 will produce a magnemotive force MMF2, which is equal to N2 times I2, and cause a flux in the core limited only by the reluctance of the core material, R. Depending on the direction that the coil is wrapped in, and it may be in this direction, we'll assume that for now, this magnemotive force, MMF2, links the primary coil, resulting in an induced current I2, which must equate to MMF2. But because there are N1 turns in the primary coil, MMF2 must equal N1 times I1. Since the magnemotive force is the same in both coils, then N1 times I1 must equal N2 times I2. Now remember Lenz's law, which states the induced current's magnetic fields oppose the change which produces it, or the induced magnetic field acts to keep the magnetic flux in the loop constant. So if the increase in current I2 will try to increase the magnetic flux, or MMF, which I've indicated by the MMF I2 arrow, then I1 will counteract the attempt to increase the flux, or MMF, by producing a counterflux, or MMF, in the opposite direction. This is Lenz's law. The net effect will be that the magnetic flux in the core will not change due to the current flowing in the secondary coil, but will remain the same, that being the magnetization flux only. We can now express the turns ratio N1 to N2 in terms of the primary and secondary currents. That is, the turns ratio is equal to I2 all over I1. That is, of course, if we are loading the transformer and there is current flowing in the secondary side. In comparison, this is the inverse of the voltage ratio, which is equal to V1 over V2. Now let's look at the power flow through the transformer. If the transformer is loaded, as is the case by adding Z2 to the secondary, we can measure the power flow into the primary by measuring the voltage V1 and the current I1 and multiplying them together to give us this equation. We can measure the power flow out of the secondary similarly by measuring V2 and I2, and that will give us the power flow out of the secondary. Now, we can take the power flow into the transformer equation and converting I1 and V1 to I2 and V2 using the turns ratio, we get this equation. And clearly, we can cancel out the turns numbers. In other words, the N1 in the numerator cancels out with an N1 in the denominator, and similarly, the two N2s can be canceled out as well, leaving us with V2 times I2, which is equal to the power out. This means that the power out is equal to the power in, which should be no big surprise because a transformer can't add power to the system. It's neither created nor destroyed. It just flows through the transformer. Let's take another look at this transformer setup with a load in the secondary of the transformer. And there's going to be current flowing in the primary as we have calculated, and there is a voltage drop across the primary coil. So the power supply sees an impedance because it's reflected due to the impedance on the secondary. And we can calculate what that reflected impedance is by measuring the voltage drop across the primary coil and the current into that coil. And that would give us the reflected impedance. In other words, V1 all over I1 is going to give us the reflected impedance. We can substitute for V1 by using the turns ratio and V2, and we can substitute for I1 using I2 and the turns ratio of the transformer to give us this equation, which is N1 all over N2 times V2 all over N2 over N1 times I2. Well, V2 all over I2 is just Z2, and N1 all over N2 over N1 is N1 over N2 squared. So Z1 is equal to Z2 multiplied by the square of the turns ratio, which is the same as A squared times Z2.
This video is part of my DIY house circuit layout and connection series. In this series, I will be covering essential topics to help you understand and manage your home's electrical system safely and efficiently. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that, in my opinion, are worth paying attention to. One of those products is the EcoFlow Delta Pro Ultra. The EcoFlow Delta Pro Ultra is one of the most versatile whole home backup solutions that has just been introduced to the market. This backup power system is designed for both extended outages and daily use, with the unrivaled capacity of 6 kilowatt hours and 7,200 watts output, and 5.6 kilowatt solar input. A single unit can run your entire home. With EcoFlow Smart Home Panel, you get an uninterrupted power supply backup, and with automatic switchover, energy consumption monitoring, and lower electricity bills. This unit is not driven by gas or diesel generation, but uses the battery storage unit that is charged when the utility is available. This means that the unit can be placed indoors or outdoors and is virtually silent when operating. It has a stackable design that can be expanded to increase output in only minutes, compatible with various energy sources from solar to gas to meet your ever-changing power needs. To attain a discount of 5% off of all EcoFlow products and more information on this subject, And to pick up your free digital copy of the Ultimate Guide to Residential Standby Generators, simply fill out the information requested when you go to this website, https://bit.ly/3 lowercase u, uppercase w, lowercase v, lowercase e, uppercase r, and lowercase h. Before we end this video, I want to repeat the connection to my free copy of the Ultimate Guide to Residential Standby Generators and the 5% discount code for all EcoFlow products. Also, here is the connection to obtain a free copy of my 50-page electrical power crib sheets. And finally, here is the link to all of my electrical courses, which are located in my stand store.